So we're back again with another lecture for engineering mechanics, statics of rigid bodies. I'm your lecturer, and we will be covering still chapter 2, force vectors. So our chapter objective, these are our chapter objectives, and for this particular lecture, our lesson would be to express force and position in Cartesian vector form and explain how to determine the vector's magnitude and direction. This one, the second one. So the first one, we already finished this, parallelogram and triangle laws. The third one, I think we cannot cover it in a matter of 1.5 hours. So we will be still here in objective 2. And from the previous lesson, we already did this in 2 dimensions. That is the x and y axis. So for this lecture, we will be doing 3 dimensions. So we will be introducing another axis we call the z axis. Okay, so I believe for you architecture students, visualizing figures in 3 dimensions is very much very essential. So I hope you pay attention and master this concept. All right, so let's begin. Okay, so still we are dealing with Cartesian vectors. So we have here a vector A. Recall that we are writing vectors in boldface. Okay, so this is boldface A, this is vector A in blue. Alright, so we can find the magnitude of A by finding its magnitude in the 3 axes shown here. So the 3 axes are just the 3 components of this vector A are simply rectangular components. So we have discussed that from previous lessons. So we'll be looking for rectangular components. So as you can imagine, we'll be dealing with still triangles, angles, but this time unlike from 2 dimensions, we only determine 1 angle. Here we will be determining 3 angles. Okay, so if you can imagine, this is your origin here. Please follow the cursor. This is the origin. This is the arrowhead of your, or the denoting the direction of your vector. In order to find that magnitude from the origin, we need to take a measurement equivalent to a sub x in the x direction. Okay, so let's go ax. This is the magnitude of the x component of a. Okay, so going here along the x direction, and we will go ay units in the direction of the y-axis. So we go from here, x, this is from our origin, going ax units, and then going ay units. And now you can imagine that our our x and y axis are just in this plane. Okay, I hope you can follow and you can imagine that this is the plane of our x and y axis. Now we added another axis called the z axis, and the z component of a would be the measurement az, the magnitude az. So we measure that going up, and that is our vector. Okay, so it's just imagine in 2 dimensions we are finding the vector. The rectangular components is x and y, so the vector will lie somewhere here. I hope you can follow the cursor. But in 3D, you need to include the third dimension z, and there you have your vector. Okay, so maybe you're curious about what's this left side in the presentation is. It's called the right hand rule. So we will be using a right-handed coordinate system. So pardons for those who are left-handed. I hope you, you can still relate. So we will be using a right hand rule. So what is this for? So this so-called right hand rule is for us to have a common basis and a common what do you call this? Okay, a common positive axis. Alright? So for two dimensions, there is no problem whether you denote um you have different interpretations of which is negative and positive axis. That's only in two dimensions, so it's not really a problem. But in three dimensions, that would be very tricky. So to simplify that, we should have a common ground of establishing which are the positive axis. Okay, so for the right hand rule, as you can see here, you can take your right hand and do a thumbs up. Okay, and here we draw our x, y, z coordinate system with your right hand. So for us, we just need to imagine it. Okay, so I hope you can imagine it. So recall that we are trying to establish or determine which are our positive axes. Alright, so I hope at this point we all agree that we will be using the right-handed coordinate system for the purpose of simplifying it and for us to have a common positive axis. Okay, so now that that is settled, see here that the direction of your thumb is pointing to z. The direction of your arm is pointing to y. And the direction of your fingers, these four fingers of yours, is in the direction of x. Okay, so that would be our positive axis. Anything opposite that would be negative. Okay, so if you do the right hand coordinate system and the direction of your vector is going opposite your thumb, that would be a negative z component. Same goes for y. So the direction of your arm going into your body here, that is positive y. So anything opposite that, that would be negative y. And the same goes for x. So x here is the direction of your fingers. Anything opposite would be negative. Okay? So that is how we determine our positive axis. So I hope everyone agrees to use this right-handed coordinate system for simplification. Okay? So now let's go to the same vector. So how do we do the Cartesian vector representation of that? So as you studied from our previous latest lecture, we write it down as the vector A in two dimensions. That would be equal to the component in x with the unit vector I plus the component in y with the unit vector j. So for three dimensions, we will be just adding the component z with the unit vector k. So again, recall, we assigned the unit vectors. So these are called unit vectors because they have a magnitude of 1 and they are denoting only the direction of the vector. So in our case, we introduced the unit vector I for the direction of x, the x component, j for the direction of the y component, and the newest addition is k in the direction of the z component. So ijk. Okay, so just try to memorize that. So you have xi, yj, and zk. So I hope you are not confused before we are dealing with f, right? for a force vector now. We're dealing with A because we will be also tackling addition of vectors. We will be having a vector B. Okay, so recalling our right-handed coordinate system, this is the direction of positive I, the direction of your fingers. This is positive J, and this is positive K. Anything opposite would be negative I, negative J, and negative K. Okay, so to write the Cartesian vector representation, this in the blue box, for vector in 3 dimensions. Okay, so imagine if you don't have a z component, meaning your vector is just lying in the xy plane, you won't be having a z component. That would be a 0 multiplied by k. That would be 0. So you're back with what we discussed previously, axi plus ayj. Okay, so I hope this one makes it easier for you to write it in 3 dimensions, because we will not only be operating on one vector, we will be operating on multiple 3-dimensional vectors. So it's imperative that you know how to write or express each of those vectors in their Cartesian vector form, so that when you need to add or subtract them, you can combine the do scalar algebra on the components which are going in the same directions. That is, having the same unit vector, or all that has I can be added, subtracted, all that has j, and all that has k. Okay, so I think you already realized that by now. Okay, so for the magnitude, I know you are very familiar with the Pythagorean Theorem, right? So you just have their c squared is equal to a squared plus b squared. That is in 2 dimensions. So for 3 dimensions, again, we will just be adding our z component here. So you have 3 squares here. Ax squared plus ay squared plus az squared. The square root of that will be equal to the magnitude of our vector, in this case, vector A. Okay, so I think I already explained earlier about this, from the origin going ax units, and then from there going ay units, and from there going az units, and then you have your 3-dimensional vector. So notice here how many triangles we generated. We have this triangle, the blue one, okay, the hypotenuse of which is the magnitude of the vector, okay, A, and it's making a right angle with the here with the z axis, and we have here another measurement, we call, or we term it a prime. Okay, so for the blue triangle, the sides are a prime and az, okay, and the hypotenuse is the magnitude of a. So now let's go to this triangle, the gray shaded triangle. It is composed of the x and y components, and the hypotenuse is a prime. So it's better that we discuss this for now, since we will be doing a lot of trigonometry later. So please try to visualize these 2 triangles. So I know it's hard to visualize 3D in a 2D space, but since we are online, we're doing video recordings, we cannot really try to display it in 3D. We are not face to face, but I hope by these diagrams you can follow, and this somewhat looks 3D for you. Okay, so that's how you get the value of the magnitude of your vector. If you know the x component, the y component, and z component, just take the sum of their squares and the square root of that, and that is your magnitude for the vector. Okay, so we discussed, we stressed in our very first lessons that we will be dealing with vectors, and vectors have magnitude, a line of action, and a direction. So to denote the direction of a three-dimensional vector, we need what we call the direction cosines. In this case, we will be introducing the angles alpha, beta, and gamma. Okay, so this is your alpha, this beta, and gamma. So what is the definition of these three angles? Okay, so the definition is these angles are the angles between our original vector and the respective axis. Okay, so for example here, this is your x-axis and this is your vector. So the angle alpha is the angle between our vector and our x component. Okay, so again, this is a matter of memorizing again. So alpha for the x-axis, beta for the y component in the y-axis, and gamma for the z component. Okay, so alpha, beta, gamma, just try to memorize that in your head. So you have ijk, you have alpha, beta, gamma, you have x, y, z. Okay, so for our final answers, since we're looking for vectors, you need to be able to express this vector along with its direction cosines. Alright, so in 2 dimensions, you only need to find one angle. So for 3 dimensions, you need to find 3 angles. So it is what it is. So notice here, we have a variable or a vector u sub a. Did you see that? So this u sub a would be a unit vector. Okay, this is the unit vector denoting the direction of our vector a. Okay, so if you have I for x, y for j, k for the z-axis, you have u sub a for the direction of our vector a. Okay, so again, I, j, k, x, y, z, and you have alpha, beta, gamma. So this direction, so-called direction cosines, are the angles that the x, y, z components make with our vector. Okay, so here, to better understand this or better visualize this direction cosines, please look here in the figure and look how many triangles we generated this time. We have the blue one, we have this orange one, we have the gray one. Okay, so for the blue one, that would be if you draw a line from the arrowhead of our vector to the arrowhead of the x component, that would give you a 90 degrees angle. So we are having right triangles. Okay, so what does that mean? It means that we can use trigonometry to determine these angles, so-called direction cosines. So for this blue one, you can see, since this is perpendicular, this angle here, you have the hypotenuse, the value of or the magnitude of a, and you have the x component, which is the adjacent side of the triangle. Same goes for every triangle here. For the orange one, ay is adjacent your beta, and for the gray one, gamma is az is adjacent to gamma, where for all the triangles, they have a common hypotenuse, which is the magnitude of a. So we all know that the cosine of an angle is equal to the adjacent side over the hypotenuse. So for cosine alpha, that would just be equal to the adjacent side, which is a sub x, the x component, all over the magnitude of our vector a. Same goes for beta angle and for gamma angle. So then we can determine the our direction cosines by taking the arc cosine of these equations. So ax over a, ay over a, az over a, arc cosine of that will give us the angle. Since in these triangles we already see that cosine of alpha is equal to ax over a, and so on for beta and gamma. So to find these angles, we just need to get the arc cosine. So we just press shift in your calculator and cosine. That would I think that would give you the arc cosine, arc sine, or arc tangent of that. So for this, that's why they are called direction cosines, right? So now you realize why they are called direction cosines, since we can find the value of this by taking the cosine of the component over the hypotenuse. Okay. So I think this is easier to memorize, but what's better is that you will be able to draw it like this and do your analysis. But during your tests, your assessments, where time is a constraint, you need to you don't really have the time to draw these triangles to prove it to yourself. So at this lecture, we already proved it, and here we presented the equations, and it's just a matter of memorizing it, but also understanding where they came from. That's why we are discussing it. Okay. So for our unit vector a, in order for our vector to be a vector, you need the direction and you need the magnitude. So our direction, or our they call this unit vector u sub a in the direction of a multiplied by the magnitude of a will give us the vector, this, the bold face one, a. So it means that we can solve for our unit vector a by dividing our vector a with the magnitude a, right? So our unit vector, we know, has a magnitude of 1, so it just makes sense, a over a, but this one is a vector, the denominator is magnitude, that will give us 1, right? Or 1 times u sub a. Okay, so let's do that on our vectors. So we can express our unit vector u sub a as ax over a I, ay over a j, plus az over a k. Or as we have learned earlier, ax over a is equal to cosine of alpha, ay over a is cosine beta, az over a is cosine gamma, our direction cosines. So we can write our unit vector u sub a as in terms of our direction cosines. So cosine ai plus cosine beta, cosine alpha I plus cosine beta j plus cosine gamma k. So this is the equation for our unit vector u sub a in the direction of a. So since we need to find alpha, beta, and gamma, and most of the time 2 will be provided and you need to solve for the other one. So for that, we have this equation. So the squares of the cosines of alpha, beta, and gamma would equate to 1. Okay, so if you're given alpha, you're given beta, and gamma is missing, you have your calculator, you can just solve it by equating that to 1. But of course, you need to have your calculator. If you don't have your calculator, you don't have gamma, you have alpha and beta, then you still can't solve the equation. Okay, so this is our equation to find the direction cosines when two of the angles are known. And that's easy. We can find the third one with this equation. So I hope you are taking notes. You have a little notebook or wherever you are taking notes and you are writing down this important equations so that you don't have to derive them when you are faced with an exam or a test. Okay, so just a review. So our vector A is equal to the magnitude of A multiplied by the direction, the unit vector in that direction. And we can write the unit vector in that direction as cosine alpha I plus cosine beta j plus cosine gamma k. That is in the previous equation here. If we multiply that by the magnitude A, this will just give us again the Cartesian vector form, which is axi plus ayj plus azk. So these are the relations between our components and the direction angles or the direction cosines. Okay, so let's introduce another concept, the concept of transverse and azimuth angles. So we're having the same vector A here, and we have here two measurements of angles. Okay, we have here the angle, this one, phi. It denotes the azimuth angle. Okay, so at this point, it's really depending on the orientation, which is the transverse and which is the azimuth angle. But since we are using our reference book, we will follow the reference book. So in the reference book, angle phi, this one, angle phi, I know you are used to angle theta here. So our angle theta, that will be our transverse angle. Okay, and the angle phi would be our azimuth angle. Actually, it's really, we can really interchange them, but for the sake of, since we're using our reference book, we will follow the reference book. Okay, so just remember that this one, the angle theta, that will be your transverse angle, and the angle phi would be our azimuth angle. So for the sake of you to not be confused, it would be easier for you. The azimuth angle phi would be adjacent the AZ or the Z component. Okay, so just that's if you say AZ and you say this, you see this angle, that would be azimuth, and the other one would be transverse. Okay, so again, let's analyze this. We have two triangles, the light blue one and the blue one. So in the light blue one, we have the angle phi, and for the blue one, we have the angle theta or the azimuth. The transverse and the azimuth. So here, the component AZ is adjacent our phi angle, azimuth angle, and the hypotenuse is A. So we can solve for AZ as A cosine of phi. Alright. On the other hand, the other rectangular component is another vector that we will term as A prime. A prime is the hypotenuse of the triangle where x and y are the components. Okay? So here, A prime is opposite the phi angle. That's why it's A sine theta. Again, it's better for you to grasp the trigo behind this so that if you forget, you can derive it on your own. But also, it would be more useful if you memorize this. Okay, so now let's look for how can we solve for the x and y components. So we have the x and y are components of A prime, which are also components of our main vector A. So for A sub x, we can solve it by this adjacent, the theta or the transverse angle. So ax would be equal to A prime cosine of theta. And we know that A prime is A sine theta. That's why ax is equal to A sine theta times A sine phi cosine theta. Okay, so I think it would be easier to understand the trigonometry behind so that you can write these equations. Or again, memorize. AY on the other hand is opposite the theta angle. That's why it's A prime sine theta. Again, we know A prime is A sine phi. That's why we have A sub y is equal to A sine phi sine theta. And if we want to write our Cartesian vector form in terms of the transverse and azimuth angle, we have A sine phi cosine theta I. That's the x component we expressed earlier, plus A sine phi sine theta j, that is this one, the y component, and the z component is just A, the cosine of the phi angle k. So just do some mnemonics in your mind, like sine cos, sine cos, where the phi angle comes first. Phi theta, phi theta, phi. Okay, I hope that works for you. I think there's no other way. Alright. Now let's go to addition of this Cartesian vectors. Again, we are so used to forces 1, forces 2 in 2 dimensions. Now let's use A, B, C, and D for our 3-dimensional vectors. So we have still the same. R, the resultant vector, is equal to adding vectors A plus B. And adding vectors A plus B, what would you do? In 2 dimensions, what we do is we take all the components in the x-axis, add them up. So here we have AX plus BX. Same goes for the y components, AY plus BY, J. So for x, AX plus BX, I plus AY plus UY, J. So this time in 3 dimensions, we just have to add up the Z components. That's AZ and BZ, and that would be in the K direction. So the same thing. The resultant would be equal to the summation of the forces. Summation forces in X, I, plus summation forces of Y, J, summation forces of Z, K. So I hope by this time, even if when you just woke up in the morning, someone asks you what is IJK, that would be XYZ. What is alpha, beta, gamma, that would be XYZ, IJK. Alright, so again, there's no other way but to be familiar with this variables that we are using. I know it's a lot, but we have no other way. That's the only way to tackle this. Alright, so we just added a third axis Z and the third unit vector K. So just imagine this from our 2 dimensions Cartesian vector lectures, and you just have to add another dimension, the third one. It's the same concept, but now you have 3 summation of forces. Okay, so now let's go to sample problem to put to use all of those relationships and formula that we derived. So this one is to express F, which is 100 pounds, as a Cartesian vector. So take note, it is in 3 dimensions. I hope you can visualize it, that it is in 3 dimensions. So here's your x, y, z coordinate system. So from the origin, going to the x in this way, going to the y in this way, going to the z, then there is your vector. So it's essentially in 3 dimensions. And we have here the angles. So in the xy plane, we have 45 degrees. So in the z plane, we have 60 degrees. So now let's go and solve this sample problem. So to solve this problem, let's do an analysis and see what we have. Okay, so here are the steps of our analysis and how we will engage this problem. And as you can see, and I hope you visualize by now, we have two triangles here. We have this blue triangle which is lying flat on the xy plane, and the light blue triangle is on the plane of the z axis. I hope you can visualize that. And we have 45 degrees for the blue triangle, and for the light blue triangle you have 60 degrees. Okay, so our first step is to name the resultant in the xy plane. So this is our resultant, which is F equals 100 pounds, but you can see here that we also have a resultant in the xy plane. So our first step is to name that resultant, and step 2, we will use trigonometry to solve for xy and z components, and that is made possible since we are given the angles. We just have to do it one plane at a time, and we will start with the xy plane. And step 3, after we solve for x, y, and z components, we will apply our direction angles to so that we can express this force as a Cartesian vector. Okay, so here is our given. So for you to better visualize that, you can see here, as we called our first step, to name the resultant in the xy plane, and this is our resultant here, f prime. Okay, so we name it f prime. So f prime is the resultant of f sub x and f sub y, which has a 45 degrees triangle here. Okay, so that's our first step, is to name the resultant. So you can name it whatever you like, as long as we don't confuse it with other variables. Of course, we have fx, fy, and fz. So if you want to call it your name or whatever, doesn't matter, as long as it's easier to write. Okay, so this would be our given, and of course we have the magnitude of f as 100 pounds. Okay, so we have 100 pounds as the hypotenuse, we have fz, and we have f prime, comprising this triangle, light blue triangle, with 60 degrees. Okay, so in order to find f prime, we can write that down as, so let me write first what is required by the problem. So what is required is the Cartesian vector form of our f, which means we need the form that is f equals fxi plus fyj plus fzk. So we write f x I. So by now I hope you already memorized this. Fy j plus f z k. And apart from that, we also need the direction angles. We need alpha, beta, and gamma. Okay, so what we are actually looking for are to give values to these variables: fx, fy, fz, alpha, beta, and gamma. So for our solution, going back again, we need to identify first and name the resultant in the xy plane, and we already called it as f prime. So here f prime, by trigonometry, this is f prime, this is let me just draw that separately for you to better visualize it. So we have actually a triangle here where this is 60 degrees. This is our f prime. This is f prime, and this is f, which is equal to 100 pounds. Okay, so by trigonometry, we have an angle, we have the hypotenuse. We can find this f prime, this side, and that would just be, this is 60. This is adjacent to that angle, so our f prime would be equal to 100 pounds cosine of that 60 degrees angle. So if you plug that in your calculator, it will be cosine 60, that's half of 100, so we have 50. F prime equals 50 pounds. Now that we know that f prime is 50 pounds, let's go to the other triangle, which is lying on the xy plane. For better view, let's draw it here. So this time, the resultant or the hypotenuse is equal to f prime. So this is our triangle, and our angle here is 45 degrees. So our hypotenuse is f prime, which is 50 pounds. And we are looking for fx and fy. Okay, so by using trigonometry, we can solve for these values. So as you can see, I just draw this triangle, but in our figure, this is that triangle. Okay, I hope you can see that. And solve for fx. So according to this triangle, fx is the adjacent side to 45. That's why we will be writing down it's 50 pounds cosine of 45 degrees, since it's adjacent, so it's cosine. So plug that in our calculators. Square root over 2 by 50. That gives us 35. So I will round off in 2 decimal places. So that's 35.36 pounds. And we have Fy equals 50 pounds it's the opposite side, so that's sine 45, but we all know that will be the same, sine 45 and cosine 45. So it means that the value of Fy is same as the value for x, which is approximately 35.36 pounds. Okay, so for Fz, we go back to the first triangle, this one, since this is Fz, right? So looking at this triangle here, this is our Fz. Okay, that is our first triangle. So Fz would just be equal to 100 pounds, and it's the opposite side, so that's Fz equals 100 pounds sine of 60 degrees. And sine 60 degrees is square root of 3 over 2 times 100. That gives us 86. Fz would be equal to 86.6 approximately pounds. Don't forget your units. Okay, so now we have our values for fx, fy, and fz. So we just need to write it down in this form right here, and also solve for these angles. But now let's analyze using our right-handed coordinate system that we are agreed earlier. So this is our vector, and if you will imagine your right hand here, let me draw a sample of a right hand here just for your reference. We have this right hand and this is the arm. Okay, so our vector, our z component is going the direction of our thumb, so it means that our z component is a positive one, right, according to the right-handed system. Also, our f of x is going with the direction of our fingers, so it means that fx is also positive according to our right-handed coordinate system. But fy, where the positive axis is our arm, the component here is going the opposite direction. It means our fy is negative. So please don't forget these signs when you write down the Cartesian vector form of our vector. So let's have another page and write down. Okay, so our vector then would have, this is, I'll try to make it look like it's boldface. Okay, so f, we just simply write our values. So we have 35.36, that is our f of x, and the unit vector is I. That's positive. Okay, the next one is a negative y, so we have negative 35.36, that would be j. And we add our z component, which is 86.6, and that's k. So since we have a unit, we enclose that in parentheses and we put our unit here. Okay, so this is the Cartesian vector form of our three-dimensional vector. But what remains, let me write that down and compile it as our answer. So this is our answer for the Cartesian vector form, but we still need to solve for the direction angles or direction cosines. So direction, so by now I believe you already memorized in your mind that alpha, beta, and gamma is referring to fx, fy, and fg. So for our alpha angle, that would be the arc cosine of fx over a, or 35, 36 over 100 pounds, and that would give us, so in your calculators, what I want you to do is not to round off, okay, since you can store the values. So that's 35.36 divided by 100, and our cosine of that, we have 69.29 degrees. So for beta angle, we have our cosine of, here, please don't forget your sign. Okay, this will just be the same with this, but it's not, because it's going the negative direction. So we have negative 35.36. That gives you 110.71 degrees. Okay, so as you can see here, your direction angle will be more than 90 degrees if your component has a negative sign. If it's positive, it will be less than 90 degrees. So for gamma angle, you have our cosine of, this is positive 86.6 all over 100, and that is approximately 30 degrees. So now that you have named your direction angles, this is now our answers. And of course, you need to draw the resultant. Let me draw that. So we have here, this is our answer. So this is our axis. Please bear with me. So this is our resultant. It's going from the origin to this direction, correct? Okay, so this resultant is F, and it's equal to 100 pounds. And let me write down, this is X, this is Y, and this is Z. Okay, so the angle that our vector makes with the x-axis, that is alpha, that's 69.29 degrees. So the angle that our okay, I will put it here, this one, the angle that our vector makes with the y, that is beta, that's 110 110.71 degrees. Okay, so notice here that if it goes the negative direction of y, it will cross more than 90 degrees. That's why we got here 110.71, and that can be denoted, or you can observe that by having a negative going the negative direction for that particular component. So the same goes for x and z axis. If they are in the negative direction, they will go over 90 degrees. Okay, so if you are given, for example, in the problem, you're given an angle which is more than 90, you can presume that that component is in the negative direction. Okay, so the angle that our vector makes with the z-axis, that would be 30 degrees. Okay, so now this is your overall solution or answer for this problem. You have the partition vector form, you solve for the direction angles, and you draw your answer. Okay, so let's have another example. So for your questions and clarifications, by the way, please, I know this no one is filling up the Q&A form, so I hope you understand it fully or not. So please utilize our Q&A form in our Google Classroom for that. Okay, so this is our answer for that previous problem. Let's go to the next. So we just rounded off here, 11169.3. Okay, here for example number 2. So as you can see here, there are two forces, F1 and F2, acting on this hook. So the problem is asking us to specify the magnitude of F2. So here F2 has no magnitude. We don't know its directions. So also find its coordinate direction angles. And our condition here is that so that the resultant force acts along the positive y-axis and has a magnitude of 800 newtons. So how are we going to tackle this? Again, we have steps here. So step 1 is to express the two forces F1 and F2 in CVF or Cartesian vector form. As you can see, F1 is pretty much complete. It has a magnitude and the angles are given. So we can readily write this down as Cartesian vector form. F2, on the other hand, is still unknown. But we are given a condition that the resultant of these two vectors acts along the positive y-axis. So it doesn't have x and z components but y component alone. So the step 2, the ijk components of the resultant force must equal the components of F1 plus F2. So we will be doing vector addition here. So we have Fr equals F1 plus F2. And by that, we will be getting an equation and we can find the unknowns. So with F2 components, we will be solving for the components of F2 from that equation. And after we get the components, we solve the magnitude and solve for the direction angles of F2. So our computation here will revolve with F2. Okay, so let's this would be our given here. So for you, I want you to handwrite it. So this is just for the purposes of having a fast discussion. So these are our known values. So for F1, we have the magnitude is 300 newtons. We have the coordinate direction angles. We have alpha. This is alpha. Let's call it alpha 1 since this F1. So alpha 1 is 45. 60 degrees is your beta 1. And 120 degrees is your gamma 1. Okay, so just by observing the coordinate direction angles, we can conclude that the z component of F1, that is F 1z is negative. And as you can see here, if you use your right-handed coordinate system, the z component is pretty much going opposite of our thumb. So for f2, we don't know anything. Okay? But we are also given that our resultant force acts along the y. How can I draw this one? Acts along the y-axis and doesn't want to be drawn, so let me try that again. Okay, here. So this is our resultant here, and it's, let's call that f sub r, and it's having the value of 800 newtons. That's our condition. Okay, so our resultant is just lying in the y direction. It doesn't have an x component, it doesn't have a z component. Okay, so for our required, what are we trying to look for? So what we want is the Cartesian vector form of f2. So we have CVF of f2 that means we need f2x y and z as well as their direction angles. So alpha 2, let's just call that alpha 2, beta 2, and gamma 2. Okay, so now let's go to our solution. Okay, where will I put that? Let me put that here. Okay, so what is our solution? Our first step should be to write the Cartesian vector form of f1. It's pretty much complete for now, right? So f1 is 300 newtons, but we don't know the components. So let's operate first on f1. So f1 would be, let's write it down here, f1 as a vector, so that's it. This is its Cartesian vector form. So we have the coordinate direction angles, and we know that cosine of alpha would be equal to f1x all over f1. So we can solve for f1x by multiplying f1 and the cosine of the alpha angle. The same goes for beta for the y component and gamma for the z component. So let's just plug that in here really quick. So the value or the magnitude of F1 is 300 newtons. And for that, we need to multiply it with 300 newtons, the cosine of 45 degrees, that's I, plus the cosine of, what's this, 60 degrees, J, plus the cosine of 120. So notice here, you don't need to do the sign convention here, because when you get the values of this, the negative sign will appear after you do the operation. So we have K. Okay, so multiply that, each of that, by 300 newtons, which is our magnitude, and we will get the Cartesian vector form of our F1. So it's important that we write it this way so that we can operate on it with a given condition that we have a resultant of 800 newtons. Okay, so that's cosine 45 by 300, that's 212 point 13 I. Next is cosine 60, that's 1/2 of 300, and it's positive, so that's plus 150 J, and we have cosine 120, that's negative 1/2 by 300, so that's minus 150 K, and don't forget to write the unit, which is newtons. So this is now our Cartesian vector form for our first one. So again, we tried to solve for that to find the components of F2 by writing this equation. So by vector addition of forces, everybody knows how that is done, right? We write the equation down as this. So let's put it in blue. So we have our resultant force is just equal to F1 plus F2. So we already have the form of both our resultant force and our F1. So we can write that down as okay, let's write it directly. So F R in vector form, that would give you 800, that is in the y axis only. So you have 800 J newtons that's equal to F1 plus F2. We just need the components and the ijk. So F1, we can write it here as the F1 component is 212.13 for the x component, and that is plus the F2 component, which is unknown. So for now, F2x, and that would give us I. So the next one would be the j component or the y component in the j direction. That would be for x, that's for F1. For y, that would be 150 plus the unknown F2 y. Okay, so I hope you can follow and you have a glimpse of what should be done later. And lastly, we have the k direction, the z component. We have for this, we have for F1 z, we have 150, negative 150 plus the unknown F2z. Okay, now that we have these equations, we can solve for the value of all of these are in newtons. Okay, so here we can solve for each one with this equation. So for the x component, we will equate it to 0 since our resultant force here have no x component, that's 0i. For the y component, we equate it to 800 since the only component our resultant has is y. For z, we will also equate it to 0 since there is no z component in the resultant. Okay, let's transfer that to another page. Okay, so for the I direction, for x or the I direction, for the resultant, we have 0, and that is equal to 212.13 plus F2x. So that's 212 so just to transpose, F2x is equal to a negative 212.13 newtons. So for y, we have 800 newtons, that's equal to 150 plus F2y. So I hope you can follow this. 150 newtons plus F2y. So solving, F2y would just be equal to 800 newtons minus 150 newtons, that would be 650. So F2y just equal to 650 newtons. That would be positive. Okay, for z, 0 is equal to negative 150 plus F2z. So that's negative 150 newtons plus F2z. So meaning that F2z will just be equal to, transpose it to the other side, that will become positive. That's 150 newtons. So from here we can write the Cartesian vector form of our force 2. So force 2, that's negative 212 I plus 650 J plus 150 K. So now this is our Cartesian vector form. Don't forget that that is in newtons. This is our Cartesian vector form for F2. What remains is to define this vector by its direction angles. But of course, we need to find its magnitude. So F2, the magnitude of F2 would just be equal to the square root of the sums of the squares, right? I hope you can recall this equation. That's 213 newtons squared plus 650 newtons squared plus 150 newtons squared, and the square root of that, and we get the magnitude of F2. So why do we need the magnitude of F2? Because we need that for the, to define the vector, of course, by its magnitude, and to find the direction cosines, because that involves the magnitude of F2. Okay, so we have, that's negative 212.13 squared plus 650 squared plus 150 squared, and the square root of that is approximately 700 newtons. Okay, now that we have the magnitude, we can solve for the direction angles. So the direction angles can be, let me just write this down, as this is our answer, of course, so I don't want to write them again, so I'll just put this section in here. Next would be the direction angles. So for alpha 2, that would be equal to the arc cosine of negative 212.13 all over 700, right? That's negative 212.13 divided by 700. Our cosine of that's approximately 107.64 degrees. So for beta 2, that would be our cosine, that's 650 all over 700. That gives us 650 divided by 700, shift cosine, that's 21.79 degrees. And lastly, for the gamma angle, gamma 2, so again, our cosine of 150 all over 700. And that's 150 by 700, that's 77.63 degrees. Okay, now we have defined f2x, f2z, f2y, and f2z, and alpha, and we have solved this problem. So this is our answer for this problem. Of course, we have to draw it. So since we will just be dealing with what do you call this, with f2, we just draw f2 if that is okay. So according to this, okay, wait, let me undo that. Let's use black. Okay, so this is our line. Yes, another line. And this is our x-axis. Okay, no, I will just display here the vector 2. Okay, so vector 2 is going in the positive y, positive z, but negative x, right? So we will be going on this. Let me draw another one. Oh, sorry, that's not the color. Okay, this is the negative x direction, and our vector should be in the positive y, positive z, but negative x, so it means it's going in that direction. So let me draw that as this. Okay, so this is our vector f2. So f2, which we found out has a magnitude of 700 newtons, and our direction angles. So for the x direction, the angle that this vector does with the x direction, that is 107.64 degrees. The angle that this makes with the y direction is 21.79. And the angle it makes with the z is 77.63. So that defines our vector now. Okay, so when you draw your vector, this is x, this is y, this is negative y, this is negative x, this is z, and this is negative z. Okay, so now this is our vector f2 that we are solving for. So the Cartesian vector form is given here, this one, the direction angles are here, and this is your vector representation, the drawing. Okay, so let me just come back in this equation if you are confused. Here we did vector addition. So in vector addition, you can only do scalar operation on the components which are going in the same direction, right? That would be x components, y components, and z components. So we equate them since the components here should equal the components of the resultant. This component x will just be equal to 0, right? Which is what we did here. Since our resultant is just have a y component. If our resultant happens to have I, j, and k direction components, x, y, z, the equations here for x would not be equal to 0. For z, it should be equal to their corresponding I, j, k components in the resultant. Okay, so I hope that is clear, and this is our answer for this problem. So again, this is the representation of our answer for this problem. We have here F1 300 newtons, our resultant is 800 newtons, and our F2 is 700 newtons. So if you want to study further, our source would still be our source material, which is Engineering Mechanics Statics by Russell Hibbeler, and this can be found in chapter 2 force vectors, pages 44 to 49 for your reference. So as always, thank you for your attention, and I hope you will work smoothly on your problem sets. So good luck.